Assalamu alaikum, dear students. We're back with another video lesson. And of course, in the previous video lessons, we talked about photoelectric. We talked about, let's say, how to find threshold frequency. And also we talked about what is maximum kinetic energy. And if you remember, we said that the maximum kinetic energy in let's say for the electrons depends on the difference between, or first of all, we said it depends on the frequency of the incident light, of course. And then in the previous video lesson, of course, we used equations and we said that the maximum kinetic energy of the electrons depends on, or it is equal to the difference between the energy of the incident light and also the work function, you can say. And we solved some questions as well. And then we ended up right at this point here. Now, of course, we have photon theory and photoelectric effect. So what can we say about photon theory and photoelectric effect? We said that if the light intensity is doubled, and of course, I remember, like in one of the parts, we answered this question. Remember this, what happens if the light intensity is doubled? How does this affect the number of photoelectrons? Remember, that is, when we talk about this one here, we assume that the photoelectric effect has already taken place. We're not, because if we're not talking about this one, for example, let's say if the light frequency, if it is not enough, no matter how much you increase the frequency, it is not going to extract or remove any electrons. So no photoelectric effect will take place. But if it's already taking place, let's say it is already happening, then what happens if we increase the intensity of light? Or what is the effect of doubling the intensity on the following? Let's say on the following. The first one is the number of photons. We know that if we double the intensity, the number of photons that is incident, that is landing, that is falling on the surface will also be doubled. Remember, because that is basically what happens. The more the intensity, the more the incident photon, don't forget. Okay, then the second thing is the number of electrons ejected. Now that is, you have to be careful when you answer this question, because we'll say after the photoelectric effect is taking place, so the frequency of the incident light, if it is exceeding, if it is bigger than the threshold frequency, then we can say doubling the intensity will double the number of the electrons that are ejected. Okay, and then the last one here, the maximum kinetic energy of the ejected electron. In the previous video lessons, of course, we did talk about this many times. We said that the kinetic energy of the electrons or electron ejected does not depend on the intensity of the light. It depends, or it rather depends on the frequency of the incident light. So doubling the intensity would double the number of photons. Let's say incident photons, doubling the intensity, it will double, or you can say the number of ejected electrons will double. But remember, assuming that the light ejects electrons, and kinetic energy will remain unchanged because it does not depend on the intensity. And of course, remember this, electrons are once, let's say, the frequency that is, for example, the frequency of the photon, if it exceeds, if it is bigger than the threshold frequency, then of course electrons will be ejected immediately, you can say, or instantly when light hits the metal surface, supporting the particle theory of light, where energy is delivered in small pockets, or you can say photons. Each photon interacts with a single electron, don't forget, so causing no significant time delay between, let's say, the landing photon and the electron extraction or ejection, you can say. Then we also said that Einstein assumed that electromagnetic waves are quantized, and we said this one in the previous lessons, or video lessons. We said Einstein assumed that, he suggested that electromagnetic waves are quantized, or basically photons, and of course successfully explained the photoelectric effect based on his idea, or electromagnetic waves are being quantized. And then of course the next point that we have, it says this led to the acceptance of quantized energy as a real physical phenomenon. The concept of energy quantization, though not observable in everyday experience, but because, or you can say, it became recognized as crucial at the sub-microscopic level, where quantum effects are significant. Okay, now we have a few Zhyar questions. Remember this. It says, when photoelectric effect happens, if the intensity of the incident light ray increases, then what happens? Remember, it says when the photoelectric effect happens or takes place. So that is, that is basically when the frequency of the photon is bigger than the threshold frequency, then increasing the intensity. Of course, will it increase the number of emitted electrons? It says the number of emitted electrons will increase, the number of emitted electrons will decrease, kinetic energy of the electron will increase, you can say kinetic energy will decrease. We said kinetic energy has nothing to do with the intensity, okay? And then so it is either A or B. This one says the number of electrons or emitted electrons increase, the other one says decrease, so the correct option it is A because it just increases. According to Einstein's photon theory, the number of ejected electrons from a metal depends on what? Remember, the number of electrons that are emitted or ejected here. We said after the electrons that are extracted, then if you double the intensity, the number of electrons, like how many electrons are ejected, will also be double. So it depends on what? We can say depends on, does it depend on the work function of the metal? Does it depend on the energy of the incident photon, or does it depend on the intensity of the incident light, or both A and B? The correct answer is intensity of the incident light. Don't forget, yeah? This is, or it says that the number of ejected electrons. It doesn't say what does the ejected electrons or how ejected, what does the ejected electrons depend on? If the question was, for example, when will the electrons be ejected, that is, or what does it depend on, then we could have said it depends on the work function, it depends on the energy of the incident photon. That is sort of kind of like we could have said this is the kinetic energy or the maximum kinetic energy for the electron, but that is not the case. It says the number of ejected electrons, don't forget. So we said the number of ejected electrons is directly proportional with the intensity. That is after assuming, let's say, the light frequency is exceeding threshold frequency. Okay, or photon frequency. According to physical or classical physics, in photoelectric effect, electron ejection depend on what? Electron ejection. That is, remember, classical physics. Does it depend on the wavelength? Does it depend on the intensity? Does it depend on frequency of the incident, or depends on both A and C? We said, of course, depends on the intensity of the incident light. That is based on classical physics. Don't forget, okay? All right. Now let's talk about something different, which is Compton shift supports the photon theory of light. So far, we're talking about electromagnetic waves as, like being quantized, photons, let's say, pockets of energy, okay? So what is Compton shift, okay? So, and remember this, Compton's hypothesis, Compton, of course, had a hypothesis. What did he say? Arthur Compton suggested that if light behaves as particle, then of course collision between photons and electrons should be resemble these collisions like billiard balls. Well, aren't we saying, for example, let's say that these electromagnetics, we consider them as photons, yeah? So Compton said that if these are considered as photon, of course, then this too, for example, it must be able to, for example, collide with electrons, and just like billiard balls, of course. So was he correct? And so what happens as for example, photon and electron interact, collide with one another? We'll say when a photon collides with a stationary electron, remember this, it transfers part of its energy to that electron. So what happens to the energy of that photon, yeah? Remember this, we have two things. We have, let's say, a photon, that is, you can call it an electromagnetic wave if we consider it that way, then it will interact with one electron or an electron. But this photon, basically it is a pocket of energy, let's say, yeah? It's a photon, yeah? So once it interacts with electrons, it loses part of that energy to that electron. So if it loses its energy, we know that frequency and, like an energy are directly proportional, you can say, or at least proportional. The higher the frequency, the higher the energy, we can say that, directly proportional. Okay, so if it loses its energy, that means the frequency will be lower. So what happens to the wavelength of that photon? How is the relationship between frequency and wavelength? They are inversely proportional, yeah? So we can say if the frequency is lower, then the wavelength for that photon will be longer, meaning that it has lost some or part of its energy. So we can say Compton shift is basically the change in the wavelength of that photon, or you can say the difference in the, or let's say the change, that'll be best if we say the change of the wavelength of that photon. That is basically what we call a Compton shift. There is a shift, there is a change in, it is wavelength, energy, and of course frequency too. Okay, so we'll say, he said that basically when a photon collides with a stationary electron, it transfers some energy and momentum also to the electron, leading to a decrease in the photon's energy. If the energy is decreased, the frequency decreases, but the wavelength will increase, okay? So you can see energy is photon's energy and frequency, but it increases in wavelength. Now, what was the experiment about? Or you can say in 1923 experiment, Compton tested this by directing an X-ray to a piece of graphite, you can say. Yeah? So what did he found? He found that the scattered X-ray, after the X-ray, let's say, interacted with the graphite, he saw or he noticed that the X-ray had longer wavelength. Why longer wavelength? We said that if they lose part of their energy, their frequency will be lower. Frequency and wavelength are inversely proportional, so the frequency lower, the wavelength gets bigger, or you can say longer than the incoming one. So the wavelength after the interaction was longer than the wavelength before the interaction. So there's a difference between the two, yeah? Confirming the shift or Compton shift prediction, you can say, yeah? So what is Compton shift? We can say it is the observed wavelength change, which is known as Compton shift. We can say it is the difference between the wavelength of the photon after the interaction minus or subtracted from, subtracted by the wavelength of the photon before the interaction, you can say. Yeah? So there's a change in the wavelength, you can say. That change, that shift in the wavelength, you can call it Compton shift, which supports Einstein's, idea or photon theory of light. And he said that, suggested that light, of course, are electromagnetic waves are photons, yeah? Then what about the direction? Like what happens to, for example, the direction of this? Aren't we talking about, we're saying part of it is energy and momentum. So we'll have to consider this photon as a particle, you can say, yeah? So we can say the wavelength shift, which depends, or like how much does it shift? How much does it, how much will it be different? How much will it be different depends on what? Which depends on the photon scattering angle, and of course, which is too small to observe with visible light, so that is why we'll have to use, let's say, a frequency that is very high, or we'll say we'll have to use a wavelength that is very short, yeah? So you might be asked a question like which one of these, let's say, light waves would be best to see Compton shift? They might give you infrared, visible light, let's say, or UV light and X-ray. X-ray would be best because you can see that it has the shortest wavelength. You can say the shorter the wavelength, the more visible or the more the significant the effect is. So we have this one, you can see. Take a look at this one. This is the incoming photon with a, let's say, certain wavelength. This is a stationary electron. Once these two, of course, interact with one another, well, this photon, let's say, collides or hits this electron, you can see that the electron will be moving in a direction. This is the direction of the wavelength here, but this wavelength that is scattered will be longer than this wavelength. Why? Because part of that energy, it is went to the electron. Less energy, less frequency, longer wavelength. Okay? That is basically, we can call it Compton shift. And if you want to define that, we'll say the increase in the wavelength of a photon scattered by an electron relative to the wavelength of the incident photon. If I summarize this one, we'll say the change, the increase in the photon's wavelength after the interaction, after being scattered with an electron, or let's say from an electron, and compared to the incident wavelength, you can say, or relative to the wavelength of the incident photon here. So these are some other questions which are very important. I would really recommend you try them as well and try to see the answer. Now, a few questions here says, what does the Compton scattering demonstrate? It basically tells you or demonstrates that photons have linear momentum and can transfer energy to electrons here. Okay, so we're leading this, of course, to something bigger, which is basically let's say 8.2 here, when we have, let's say, the interaction between photons and electrons. When you, for example, give, let's say, energy to the electrons go to a higher state, yeah? So, but this would not happen if there is no interaction between photons and electrons. So when photons collide with an electron, it loses part of it as energy to the electron. This is how and why electrons will jump to a higher state of energy and will be excited. Okay, so once again, what does this demonstrate? It demonstrates that, of course, photons have linear momentum and can transfer their energy to electrons. Okay, now we have question 10 says, a photon is deflected by a collision with a moving electron. Can the photon's wavelength ever become shorter as a result of the collision? Now, before answering this, let me explain the question to you. Normally, we say after a photon interacts with an electron, it loses part of energy. If it loses part of its energy, the frequency gets lower, so the wavelength gets longer. But can the opposite happen? If you have a photon, let's say, can it interact with an electron, and instead of reducing its energy, can it gain energy from the electron? If it gains the energy, then of course the frequency will be shorter. The frequency will be higher, but the wavelength will be shorter. So can this ever happen? The answer is yes. It can happen if the reverse of Compton shift happen. For example, instead of photon losing energy, if it can gain energy, then of course this can happen. So we'll say yes, in a reverse or in reverse Compton scattering, a photon's wavelength can become shorter if it gains energy from the moving electron. Okay, now section review 8.1 says, describe the conflict as the ultraviolet catastrophe and how did Planck resolve this conflict? How does Planck's assumption depart from classical physics? Remember ultraviolet catastrophe, yeah? Classical physics suggests that the radiation would increase, let's say, indefinitely as the wavelength decreases, you can say, yeah? Or if I say correctly, we can say classical physics predicted radiation would increase indefinitely as it approaches shorter wavelength here. Yeah, they said that the infinity of the radiation becomes infinite, never ending. Yeah, but experimental data show the otherwise. They said that the radiation, for example, increases until it reaches a peak, and then after that, as the wave gets shorter and shorter, at some point, let's say that radiation, of course, you can say the wavelength gets shorter. Let's say the radiation gets less and less until it approaches zero. That was the conflict between classical and experimental data. And of course, it happened at the ultraviolet region. That is why we call it ultraviolet catastrophe. Okay? And then Planck resolved this by assuming that the energy is quantized, which classical physics considered energy to be continuous. Okay, now another question which is very similar to what we have solved. It says, what is the energy in electron volt, right, carried by one photon, that is quantum number 1 of violet light that has a frequency of this much here. So we have the wavelength, the wavelength of this much. We have the wavelength, we have Planck's constant. Find what? Find the energy. We know that energy is equal to hf, h Planck's constant times the frequency. But now, or here we have the light, let's say, wavelength instead of the frequency. So we'll just say frequency equal to the speed of light, or light speed over the wavelength, and then multiply by Planck's constant, and that is basically what it is. Speed of light, frequency times wavelength, frequency equal to speed over the wavelength, so we'll find this one here, that is the frequency. Now, plug this number into the energy equation, that is Planck's constant times frequency. We'll find the energy in joules, don't forget. But if the question ever asks for, let's say, to find the energy in electron volt, then of course we'll have to divide by 1.6, which is basically right here, you can say. And by the way, it says, take a look. The question says, what is the energy in electron volt? So it is a must. We'll have to convert it to electron volt. So once you find the energy in joule, just divide by 1.6 times 10 to the power negative 19, and that's it. All right, now question 3 says, what effects did scientists originally think that the intensity of light shining on the photosensitive surface would have on electrons ejected from that surface? How did these predictions differ from observations? Like if we're talking about classical physics, they said doubling the intensity would double the number of the electrons ejected. That is classical physics. But the observation had a different saying, yeah? I mean, like after we observed let's say the results of an experimental data, we saw that increasing the intensity will only act or will be effective only if the frequency of the incident photon, let's say, is bigger than the threshold frequency, then doubling the intensity will double the number of the electrons ejected, you can say. All right, so scientists thought that a higher light intensity would increase both the number of electron ejection and, of course, their energy, but of their observation showed only the number of ejected electrons increased with intensity, and that is after the incident frequency is higher than the threshold frequency, while their energy depended on light frequency. That'll be the kinetic energy, we can say. How does Einstein's theory of electromagnetic waves are quantized explain, in fact, or the fact that the frequency of light rather than the intensity determines whether electrons are ejected from a photosensitive surface? And of course, we said that Einstein's theory explains that electromagnetic waves are quantized into photons, let's say. And of course, if the energy, let's say, of these photons is proportional to their frequency. So for electrons to be ejected, of course, the photon must have sufficient amount of energy, let's say, which depends on what? Depends on their frequency, let's say. Therefore, only light, let's say, with high enough frequency can eject electrons from surface of certain metals. You can say, and thus, higher energy of photon, of course, can eject electrons regardless to their light intensity. So like we said earlier, many times, if the intensity, if the frequency of the incident light, if it is not, let's say, bigger than the threshold frequency, no matter how intense the light, how big the intensity of the light, it will never eject electrons. Now, another question that we have, it's also interesting, says, light with a wavelength of this much shines on tungsten, which has a work function of this much electron volt. Remember, convert this one to joules. Are electrons ejected from the tungsten? If so, what is their maximum kinetic energy here? So we have two things here. We have the wavelength, but what do we use this wavelength for? We'll find the frequency with, then after that we'll have, let's say, the energy, right, of the incident photon, and then we'll let's say minus the work function, because the question says what is their maximum kinetic energy? Yeah? So we have work function. So normally maximum kinetic energy equal to energy of the incident minus the work function. So we have it here as well, but we can say maximum kinetic energy, it is equal to what? Maximum, it is equal to energy of the incident, that is basically hf, minus work function, that is hf naught, okay? So this two, we have this one in electron volt converted to joules, and you have, instead of frequency, we have, let's make this one smaller. Instead of the frequency, we have wavelength, all right? So we can say hc over the wavelength. So you will subtract the two, you'll get maximum kinetic energy. Okay, so what is the second part of the question? Are electrons, before that, before finding the maximum kinetic energy, the question says, are electrons ejected from the surface? So we'll have to check some numbers, yeah? First of all, we'll have to find the frequency of this incident light using that wavelength. So we'll do this one the second step, yeah? So what about the first step? We have speed of light and all that, so we'll find the frequency of the incident light, which is speed over the wavelength. We'll get a certain frequency, yeah? That is clearly in hertz. And then we have the work function, yeah? But that is in electron volt. You will have to convert that work function into joules. So, and after that, that is basically, let's say, this much in joules, after the conversion. Then we'll find the threshold frequency, which is equal to whatever the energy in joules divided by Planck's constant, we'll get another frequency, but that is the threshold frequency. Now you'll compare these two frequencies. If this frequency of the incident light, if it is bigger than the threshold, then of course it will eject electrons. If it is not, it will not eject electron. Then for the second part, it says, what is the maximum kinetic energy? Now you have these frequencies, you just subtract the, let's say, energy of the incident photon minus the threshold or the work function, you'll find the maximum kinetic energy. Once again, you'll find it in joules, but don't be surprised if they ask you to find the energy in electron volts, which then you will just divide by 1.6 times 10 to the power negative 19. Okay, moving on. We have a question or another question that is critical thinking. It says, is the number of photons in 1 joule of red light, which has a wavelength of 650 nanometer, greater than, equal to, or less than the number of photons in 1 joule, but of blue light, which has a wavelength of 450 nanometer? Explain. Now, before you look at the answer, you tell me which one do you think that would have a bigger amount of energy. So the number of photons, it says, is the number of photons in 1 joule greater of red light, let's say, is greater than, less than or equal to the amount of photon in 1 joule of blue light. Clearly, blue light has a higher frequency. When we say higher frequency, that means higher energy. So we can say the energy of 1 photon of blue light will be bigger than the energy of 1 photon of red light. And of course, you can, without going through all that, you can tell by their wavelength. We know that the longer the wavelength, that means the less the frequency. The less the frequency, the less the energy. So the one with lower or shorter wavelength means higher frequency means higher energy. And that is, of course, would be for that. Okay, now regarding 8.2 here, I was planning to do this one in a different session, but of course we have about some time, so we'll go through this one here too. So now we have models of the atoms, yeah? So we are going through the models of the electron, for the atom, not of the electrons. Like, how did the models start? What did scientists think of the atoms, let's say, and then how did their thinking progress over the time? So we'll start with, let's say, early models of the atom. What are the beginning models of the atom? Like, what do scientists say, assume, thought about the atoms? We'll start with pre-Newtonian model of the atom. Like scientists, like let's say before Newton and all that, what did they think about the model of the atom? They viewed atom as tiny, something small, hard, something rigid, let's say, indestructible sphere, a sphere that cannot be destroyed, that cannot be, let's say, cut in, let's say, into pieces, or let's say more likely something you cannot crack open to see what is inside. That is what scientists, let's say, thought, that is, let's say, prior to Newton. Okay, that would be for that. And then, of course, we have something else, which is relevance to kinetic theory. Yeah? So what did this model, or what is the relation between this and the kinetic theory? Of course, you can say sort of connected, because this model of what they say, it is supported, or you can say the kinetic theory of gases. That is this. And then, but after all, you can say discovery of the electrical nature of atoms, like atoms, like for example, let's say can be, let's say atoms can be positive or negative. We're talking about ions here. So if atoms required updates of atomic models here. So this model, what they have said, was not enough, because now they've discovered new things, so they needed to update the theory. Okay, then of course, discovery of electron. In 1897, the electron was discovered. Now, one of the models that we have, it is Thomson's model here, or you can say J.J. Thomson. So he considered atoms as, let's say, plum pudding, or you can say watermelon seed and all that. But let's just go through the detail here. In 1897, Thomson proposed a new model where electrons are embedded within a spherical volume of positive charges. What did he say? He said that atoms are basically like a spherical shell, for example. Yeah, these spherical shells are basically all are positive. Yeah, and then of course we have electrons. You can say these electrons are embedded, or like almost like stuck into, for example, the sphere. Just like, for example, think of a watermelon. And then now we have the whole watermelon, yeah? And think of the seeds of the watermelon, which are embedded, or which are, let's say, put into the watermelon there. Okay, that is what he thought, or what he suggested about the model of atoms, yeah? So once again, he said electrons are embedded within a spherical volume of positive charge. So we have something, a volume that is full of positive charges, and there are electrons there. Perhaps in other books you might see this. He said that it looks like a plum pudding, for example, like a pudding with, let's say, plums and whatever that covers, for example, that could be in that. Okay, so this arrangement, of course, similar to seeds in watermelon, you can say. So, of course, in Thomson model of atom, you can say electrons are embedded inside large region of positive charge, like seeds in watermelon. So consider this as a watermelon. I hope you're not hungry though. So these are basically the watermelon. I hope it looks like a watermelon to you. And these electrons are like the seeds of that watermelon. So the entire sphere is positive while the electrons are negative. That is basically one of the theories about the atom. And of course, now we have another theory about the atom, which is Rutherford's, you can say, theory. Yeah? So what did Rutherford propose? He proposed a planetary model of the atom. So what did he propose? He said that electrons revolve around the nucleus inside atoms just like planets revolve around the sun. All right, let's go through the detail. The concept was Rutherford proposed a planetary model of the atom with electrons orbiting around the nucleus or a dense central nucleus similar to those, or you can say similar to a miniature of a solar system, like a small solar system within the atom. Considering the sun is the nucleus, that is very small, let's say very dense, and then the electrons revolve around the nucleus. Okay, but then we have, of course, the Geiger-Marstein experiment. There was an experiment which led to that, let's say, theory. So to challenge and test the validity of Thomson's atomic model, Hans Geiger and Ernest Marstein, under the Rutherford supervision, you can say that was their students, you can say, considering Rutherford were their supervisor, they projected a beam of positively alpha particles targeted to, let's say, gold foil, okay? So what did they do? They projected a positively charged alpha particles consisting of 2 protons and 2 neutrons at a thin metal foil. So what did they do exactly? They targeted alpha particles, which consisted of 2 protons and 2 neutrons, yeah, into a thin piece of gold foil. So what did they notice as a result of this? They saw that most of these alpha particles went right through the atom, right? Or you can say, of course, the gold foil. But also they saw that some of these particles were scattered back. You can say some of these are scattered at an angle, some of them bounced back at 180 degrees. So what did they say, or what was the conclusion of this? And of course, they said that based on this, because the alpha particles are positive, so they said that if that is the case, then there must be something very heavy and very dense inside the nucleus. And that thing, because some of these particles were scattered, deflected, if it was negative, it would have been attracted to the nucleus. So based on that, they said the nucleus must be positive. And also because most of the particles went right through, they said that most of the nucleus must be empty space. Otherwise, how is it possible that all these particles can penetrate, can pass right through the atom? Yeah? So this is basically what they said. Or if I just walk you through the conclusion, they said that the atom is positive charge and most of its mass is basically are concentrated in a small tiny region that is called nucleus. Yeah? Electrons occupy a larger volume, but not the electrons themselves are not very big, they're small. Yeah, you can say, but just the space they move around the nucleus is too large, you can say. And of course, they occupy a large volume outside the nucleus. The alpha particles that were deflected or bounced back were those that passed close to the dense nucleus, while most of the particle passed through the empty space. And of course, that had an impact, let's say, on atomic theory and all that. But I believe knowing this would be fair enough for now. Next time, inshallah, we'll continue with Rutherford's model and unstable atom. Like, was Rutherford's model, was it complete? The answer is no, of course. Like, each one of these models, of course, they were mentioning something very good. They had pros and cons, or you can say they had some flaws. And of course, these flaws over time were filled, or you can say fixed. But that will be for the next session. Till then, keep practicing, and I'll see you.